Hello everyone, my name is Chalana, and today I'll be presenting our final year project titled Driver Drowsiness Detection. Using deep learning, drowsy driving is one of the leading causes of road accidents worldwide. When a driver becomes tired, their alertness decreases and their reaction time slows, often without them realizing it. Our goal in this project was to design a computer vision-based system that automatically detects early signs of fatigue by analyzing facial cues such as eye closure and yawning. To achieve this, we developed and compared several deep learning architectures, including a baseline CNN, a transfer learning model using MobileNet v2, a CNN LSTM hybrid, and an EfficientNet VIT advanced model. After evaluating each approach, we identified the most accurate and efficient solution for real-time driver drowsiness detection. Before training, we focused on building a pre-processing pipeline to clean and standardize the dataset. We used the yawning and eye state dataset from Kaggle, which contains around 2,000 labeled images, categorized as open eyes, closed eyes, yawn, or no yawn. We started by detecting and cropping faces using OpenCV HAR cascades, ensuring the network focuses on the key facial region. Next, we resized all images, 64 pixels for the CNN and 224x224 for transfer learning models, and normalized pixel values between 0 and 1 to increase diversity. We performed data augmentation such as random flips, small rotations, and brightness adjustments. Finally, we split the dataset into 70% training, 20% validation, and 10% testing, ensuring balanced class distribution. These steps prepared the data for stable model performance and prevented overfitting during training. Our first model was a baseline convolutional neural network, built completely from scratch to establish a performance benchmark. The architecture includes 3 convolutional layers with 32, 64, and 128 filters, each followed by batch normalization, ReLU activation, and max pooling. After flattening the feature maps, we added a dense layer of 128 neurons with dropout 0.3 to reduce overfitting, and finally, a soft max output layer for 4-class classification. The model was trained for 20 epochs using the Atom Optimizer with a learning rate of 0.001 and batch size 64. Despite being a relatively simple architecture, the baseline CNN achieved about 90% accuracy on the test set. This result validated that our pre-processing, pipeline, and dataset were effective. The baseline model served as an important foundation for understanding the dataset's behavior before moving on to more complex architectures. After establishing a strong baseline, we implemented transfer learning to leverage pre-trained models such as MobileNet v2 and ResNet 50. We began with MobileNet v2, known for its lightweight and efficient design suitable for embedded systems. We imported the pre-trained base, froze its early layers, and added a custom classification head consisting of global average pooling, dropout, and a dense output layer for our 4 classes. In the fine-tuning phase, we unfroze the top 30 layers and trained them with a lower learning rate of 1x10.5. This approach improved accuracy to about 93% and sped up convergence, nearly 3 times faster than the baseline CNN. We also tested ResNet 50, which uses residual skip connections to overcome vanishing gradients, reaching 94% accuracy. These results proved that transfer learning significantly boosts model performance and reduces training time when working with smaller datasets. While CNNs and transfer learning models performed well for static images, they couldn't fully capture temporal pattern, for example, continuous blinking or yawning sequences. To address this, we designed a CNN LSTM hybrid model, combining the strengths of both architectures. In this setup, CNN layers wrapped in time-distributed modules extract spatial features from each frame, and an LSTM layer with 128 units learns the temporal sequence relationships. This approach allows the model to detect changes over time, not just individual frames. We trained the CNN LSTM with dropout 0.4 and categorical cross-entropy loss, achieving around 94 to 95% accuracy. It notably reduced confusion between open eyes and closed eyes, demonstrating that temporal modeling improves the system's real-time reliability and robustness. After testing the CNN LSTM model, we advanced to our final and most powerful architectures, the EfficientNet B0 and Vision Transformer VIT models. The goal was to explore modern networks that combine accuracy, speed, and computational efficiency. EfficientNet introduces a compound scaling method that uniformly scales the network's depth, width, and resolution using fixed coefficients, resulting in high performance with far fewer parameters. Our EfficientNet B0 model, trained for 25 epochs with early stopping, reached about 96% accuracy, the best among all models. On the other hand, the Vision Transformer, or VIT, replaces convolution with self-attention. It divides each image into small patches, embeds them as tokens, and processes them through multiple attention heads, similar to how language models process words. This enables VIT to focus simultaneously on key regions like the eyes and mouth, although VIT required longer training and more computational power. It achieved results comparable to EfficientNet, confirming that attention-based architectures are effective for facial state recognition. Together, EfficientNet B0 and VIT demonstrated state-of-the-art performance, balancing scalability and adaptability for real-time driver drowsiness detection. After training all models, we compared their overall performance based on accuracy, precision, recall, and F1 score. The baseline CNN achieved 90%, Mobile NetEV2 93%, CNN LSTM 94%, and EfficientNet B0 reached 96%. Accuracy.EfficientNet also achieved the best processing speed, under 50 milliseconds per frame, making it ideal for real-time detection. Our learning curves showed smooth convergence without overfitting, and confusion matrices confirmed fewer misclassifications between similar facial expressions. In summary, EfficientNet B0 and CNN LSTM were the most effective architectures for our goal. In conclusion, our project successfully demonstrates that deep learning techniques can accurately detect driver drowsiness through facial analysis. Among all tested architectures, EfficientNet B0 achieved the best accuracy-speed balance, while CNN LSTM provided excellent temporal consistency. For future work, we plan to train on continuous driving videos, integrate head pose estimation, and deploy a lightweight version on a Raspberry Pi for in-vehicle use. We believe this system can make roads safer by preventing fatigue-related accidents through timely drowsiness alerts. Thank you for listening.